students to another class of Prestressed concrete. Today we are going to learn about how can we design uh, prestressed poles. Uh, what we mean by prestressed poles is basically like you may have seen the light post in your neighborhood areas, right? Which are probably made of concrete or maybe a hollow cylindrical steel structure. So in this case, we are going to design similar kind of poles, which are mainly used for electrical transmission. Uh, so we are going to we are going to try to design that kind of prestress poles, and obviously in this case, the pole will be prestressed using high strength tensile steel wires. So first, before we go into this, we need to understand, we need to visualize how these prestress poles actually look like, right? So it is mostly no different than your regular poles that you see, right, in your daily life. So if you see this diagram, so in this diagram, this is basically a sample prestress pole which has been shown. All right, and the cross section can be varied, can vary across based on the preference of the designer. It can be square, rectangular, polygonal, tubular, whichever the ground situation favors, that kind of uh, cross section may be used. Okay. So obviously, if we want to design this kind of prestress poles, we need to understand uh, what are the critical loads that will be coming onto this prestress poles, right? So whatever load will be coming, based on that, we have to design the structure accordingly. We have to find out how much moment is coming, and based on that, we have to design. So usually, what happens? These prestress poles are mostly experiences wind loads, since it is a tall structure. uh, Probably it may be 10 meter or more in height. uh, so obviously there are not much of a dead load or live load it has to take. Obviously self weight as a dead load is there, but predominant loading is mostly due to the wind load. Wind load, by wind load, what do I mean? Wind load means in the face, in the vertical face, the wind blast it actually experience, that I'm talking about. And also these prestress poles will be supporting uh, electrical transmission wires. Like if you see this diagram, in this diagram, on the left side of the uh, pole there is one wire, on the right side there is another wire, right? So these prestress poles has to carry the electrical transmission wires, and obviously these transmission wires uh, has certain tensile load within itself as well. So we have to consider that as well. In case any of the transmission wires snaps, right? In that case, that will lead to unfavorable loading conditions. Like, see, both sides are now equally balanced due to the tensile load on each side, right? So if one of the, say, right side of this uh, transmission wire snaps, that means it breaks away or something like that, and the left one is the only one that is connected, then there is certain eccentric loading on the structure as well. So we have to consider that as well. In certain cases, it may lead to generation of torsional loading in the prestress pole. So we have to take into consideration of that as well. All right. So today we are going to design, and what are the most design considerations that I just discussed? Obviously bending due to wind load uh, on the cable and the exposed face. One more thing I missed, that is wind load on the cable. I just talked to you about the wind blast, that if you see this diagram, this is the wind blast that is uniformly acting on the exposed face of the prestressed pole, right? There is also a wind load that will be acting on the transmission wires. See, this transmission wire, this is having certain diameter, maybe say 5 millimeter or 10 millimeter in diameter it may be. So in that case, that small amount of diameter over a particular length, over a long length, like these prestressed poles are spaced apart spaced apart by 50 meter, 100 meter or more. So that huge length of 5 millimeter or 10 millimeter diameter will experience certain wind blast. So that wind blast, obviously the transmission wires cannot carry, that has to be carried by the pre-stress poles. We have to take into consideration of that as well. So how we are going to do that's we are going to learn when we solve this problem. But let's look into what are the design consideration. Obviously, bending due to wind load on the cable and on the exposed face. uh, Combined bending, in certain cases combined bending and torsion due to eccentric snapping of wires. uh, what is eccentric snapping, I'll come to that as well. Maximum torsion due to skew snapping of wires, bending due to failure of all the wires on one side of pole. So any condition that may be generated due to, you know, uh, unfavorable conditions for the uh, pole, so that we need to look into as well. So yes, so this is basically like you have to design the uh, pre-stress pole considering all the unfavorable conditions, and basically the most common condition, that is wind blast on the exposed face and wind blast on the transmission wire as well. So we are going to do a simple problem. uh, in the problem, it is given a partially prestressed pretension mast is to be designed to suit the following data. Spacing of poles, that means how much distance the poles are spaced apart. Like I mentioned, it may be 50 meter, 100 meter or more. In this problem, it is given 100 meter. Freestanding height of the pole above the ground, that is from ground level to the top of the prestressed pole. You have 10 meter of length, 10 meter of height. The pole is to carry twin conductor high voltage lines 60 centimeter apart on a cross tree at 9 meter above the ground. Right, twin conductor, that means two transmission wires on left and right, and they are spaced apart of by 60 centimeters. So this distance you are seeing, this is 60 centimeter, and it is located at a height 9 meter above the ground. So this is the ground level. So from here it is 9 meter, and there is additional 1 meter to the top of the prestressed pole. Conductor size, effective overall diameter is 10 millimeter. Like I mentioned, it could be 5 millimeter, 10 millimeter or more. So in this case, we have diameter of the conductor or the transmission wire as 10 millimeter. Tension in each conductor, uh, obviously there will be some tensile load within the wires, within the transmission wires as well. So it is given as 5 kilonewton. This data will be required obviously for when maybe there occurs a snapping of wires, and you have to then take in the tension load and calculate the torsion that is coming to the pole. Okay. The poles are to be located in Mangalore. Wind pressure for this zone is IS. Sorry. If according to IS 875, it is given that wind pressure for this zone is 10 Newton per millimeter square. 28 the cube strength, 50 FCK is 50. Uh, Modulus of elasticity of concrete 40. So these all data are that will be required during the problem. Loss ratio 0.7. Permissible stresses in concrete under surface load is also given. So the first thing that we are going to do in this case to try to design the uh, section, we are going to consider the most common case, that is the wind load on the exposed face and on the transmission wires. Okay. Okay. Now, coming to the design first, we have to understand how much force due to the uh, wind load that is coming onto the structure. Okay. So if you see this diagram in the problem, it is already stated that the wind intensity is 10 Newton per millimeter square. So if you convert into kilonewton per meter square, it kind of becomes 1 kilonewton per meter square. So this wind plus is acting throughout the height of the structure, right? And if you calculate this value to one singular load, in that case it becomes 1.5 kilonewton. So how is it coming? I'll just, how am I able to calculate it? I'll just show you. Just before that, we have to assume the width of the prestress pole that we are going to take. So in this problem, it is assumed to be, see, assuming the width of the pole to be 150 millimeter. That is the exposed phase. Exposed phase, that is going to this phase. Width of this phase is taken as 150, 150 millimeter. So we have to assume that first, and then simply, uh, if we just calculate the area of this phase on which the wind blast is coming, and then multiply with the intensity, we'll simply get the overall total load that is coming due to the wind blast. So let me just try to calculate this value using this calculator here. So I have a width of 150 millimeters, that is 0.15 meter, into multiplied with what is the height? Height is 10 meter, right? So 1, so obviously 10 into 1000, that is 10,000. Sorry, uh, 10 meter that going to take, not in millimeter, only in meter. So 10 meter multi, that is my area, that is 1.5 meter square is my area, and then basic wind pressure is 1 kilonewton per meter square. So multiply with 1. So you have, in that case, you have 1 kilonewton, that is the overall total load that is coming onto the face of the structure. Next thing that we need to calculate is how much these twin conductors are, how much load these twin conductors are experiencing, and then it is transferring the load to the structure at a height of 9 meter. So it is calculated to be here 2 kilonewton wind force on wires. So again we are going to calculate the diameter of the wire is given as 10 millimeter in the problem. All right. So that 10 millimeter phase will be experiencing the wind blast. So we have 10 millimeter, that is, let me just clear it out, 0.01 meter. 10 millimeter means 0.01 meter multiplied with, sorry, right, 0.01 meter into the poles are spaced at 100 millimeter apart, right? So a single pole will be take the load of wind blast on the wires 50 millimeter, 50 meter to the right and 50 meter to the left. So that then you have a length of how much? 100 millimeter. So your exposed face area on the wires is approximately 0.01 into 100. Okay. Then you have two wires. So total area is 2 multiplied with 2. So then you have, in this case you have how much? Obviously 2 meter square area, and this 2 meter square area will be experiencing a wind pressure of 1, multiply with 1. So obviously you have 2 kilonewton. So you see how this 2 kilonewton load is coming here. So this 2 kilonewton load will be acting at a height of 9 meter from the ground level. So now we have to calculate what is the amount of moment that is coming at the base. Okay, we have to simply know what is the moment that is coming into the base. So it's pretty simple. uh, 2 kilonewton load at a height 9 meter. So the moment due to that would be 2 into 9 equals to 18. So you have 18 kilonewton meter moment there. Then you have moment, additional moment due to this basic maximum wind pressure, where the total load is acting at a height of central height of 5 meter. The total height is 10 meter on which the load is distributed, and when you calculate the total load, it is coming out to be 1.5 kilonewton, and obviously it will be acting to the center of the distributed load, and that is at a height of 5 meter from the base. So you have then 1.5 multiplied with 5 equal to 25.5 kilonewton meter. Okay, now coming back to the problem, see, the maximum working moment in this case at the ground level is 25.5. So I'll just showed you how this moment calculation and load calculation is happening. Okay, and they have just skipped it here. So uh, so you have a maximum working moment of 25.5 kilonewton per kilometer meter. All right. So now they have referred to certain expression which has been previously recommended by scientists, journals. This expression that is shown here is already tried and tested. So they have simply taken that expression, and they have found the section modulus with respect to top and bottom using this formula. So MD is the working moment, FCW is the permissible compressive stress, and FTW is the tensile stress in concrete. So these two are given here as well. So if you just substitute the values, you will be able to find out the section modulus, and using the value of the section modulus, you can simply calculate the overall depth of the section. Since you already have the width, you have already assumed the width to be 150 millimeters. So if you found the section modulus, you simply know that section modulus expression in case of rectangular section is BD square by 6. Okay, so simply you use this expression and then find out the overall depth. Okay, so in this case, overall depth is required, that is required is turned out to be 300 millimeter. So obviously we will not directly provide 300, we are going to provide just a tad bit above 300. So in this case, it is provided to be 320 millimeter, okay, at the base of the section. Then you calculate the pre-stressing member at the tensile section, how much is coming out to be u FTW plus MW by Z. MW is the working moment, Z is the section modulus, and this eta that they have calculated, they have just simply taken into consideration the loss factor. Okay, so this loss factor has been taken into consideration. 0.7 is the loss ratio. Now the pre-stressing member is coming to be 7.5 Newton per millimeter square. From using this pre-stressing member, we are going to calculate the pre-stressing force. You have a section of 150 by 320. You simply use that, and then initial pre-stressing force that needs to be required in this case comes out to be 360 kilonewton. Now we have to distribute this 360 kilonewton into the 5 millimeter wires. Okay, so the area of the 5 millimeter wire is 19.6 millimeter square, and this is the permissible force that we are going to calculate. So this zero point 0.8 multiplied with the ultimate tensile strength of the wires, ultimate tensile strength of the wires is multiplied with zero point 0.8. Since we are going to calculate the permissible force, we are not going to calculate the ultimate force at which the wire fails. So then there you have the permissible force 25 kilonewton, and then you distribute this load over how many wires would be required, and it's coming out to be 14.5. So you round it off, you take 16 wires are provided at the base of the section, and the arrangement looks like this. Now coming back to the next step, we have check for limit state of collapse, like we already designed the section having 320 and cross 150 millimeter dimension at the bottom, and it has been varied throughout, and at the top it is 200 cross 150, that 320 becomes 200, since obviously the higher you go up, the lesser amount of moment the section has to take. All right. So it has been varied accordingly. Uh, so you have to simply check whether the section satisfies your limit state of collapse or not. All right. So for this, uh, we need to simply go through the IS code, that is for the pre-stressed concrete design. The code is IS 1343 and the version is 2012. All right. So you have to do limit check of collapse. You have to go to uh, at the end of the almost at the end of the code. Here, basic simple steps are provided to calculate the moment capacity of the section. All right. So in this section, you simply have to find out the this ratio, that you are having in the problem, AP FP divided by BD FCK. What is AP? AP is the area of steel in one single phase or in the tensile zone, as in case of, you remember, for RC structure. So AP is the area of steel that is available in one particular phase of the member. FP is the ultimate tensile strength or the characteristic strength of the pre-stressing steel. BD are the dimension, and FCK is the obviously characteristic strength of the concrete. So once you find out this ratio, all right, this ratio will lead you to finding FPU. FPU is the ultimate tensile stress in the tendons, that is said. So it will give you this particular ratio, using which you will be able to find out FPU. Just see here in the in the expression for the moment, you need the value for FPU, you need the value for AP, and obviously XU. FPU you have to find out from this particular ratio. AP you already know, you have the data with you, and XU that you need to find out in case of pre-stress section. Uh, how can we calculate? Simply using this ratio here. So what you're going to do is you simply find out this ratio AP FP divided by BD FCK, and using that ratio you find out FPU and then XU. All right. So you just have to keep in mind that our problem is of pre-stressed pre-tension mast, so pre-tension pole. So in this case, see the conditions at the ultimate limit state for rectangular beams with pre-tension tendons or with post-tension tendons having effective bond. So pre-tensioning is our condition here. So let's try to find out the ratio of AP/FP divided by BD/FCK. So here you see this ratio is found out. You see AP, how you are finding it, for each 9 millimeter wire, sorry, 5 millimeter wire, you have the area of 19.6 millimeter square. So on each face, if you come here, on each face you have 8 wires, right? So simply 8 into 19.6, you have 156.8. FP is 1600, and simply substitute the values. All right, 150, and this depth 282.5, this is the effective depth that has been considered, keeping in mind that you have a total depth of 320, and uh, you have this one side of wires, you consider a central position of the what can we say, a CG of all these wires will reside within this particular line, right, at a central distance of this 25 millimeter. So if you want to calculate the effective depth, you simply have to do 320 minus 25 and then another 25 by 2. So if you calculate that, you will find out it comes out to be 282.5, and FCK is in the given problem, it is 50. Alright, so the ratio we found out is 0.118. Now if you simply uh, go to this chart, you have to interpolate a bit. If you interpolate it, if you interpolate, you will find out that FPU divided by 0.87 FP is 1. From there you find out FPU, they have done it here only for 1, and then FPU comes out to be 1392. And obviously then you find XU by D for pre-tensioning case. XU by D in this case they have interpolated to be 0.24, and simply sub multiplying that you have the XU value. Now simply a very simple step, substitute all the values of the parameters in this expression and you find the M, the moment of resistance of the rectangular section. Alright, so you have a moment capacity of 55 kilonewton per meter, and the load factor against this collapse is like the capacity is 55 and the moment is coming out to be 25.5. So it's basically a factor of safety, how much load factor against collapse is there. So it's 2.16, which is pretty good. Now the next thing that can be done here is the check for the moment against in the transverse direction, right? Up to this point we have considered this as depth and this direction as width. All right, but the other way around is also possible in certain cases. If we take it, say this will be our depth and this will be our width. So in that case you have to calculate your you have to calculate your again the ratio AP/FP divided by BD/FCK. B in this case is 320 and D if you calculate will be coming around 105. You find out the ratio, you find out FPU, you find out using the same method XU, and then find out the moment of resistance against the other direction. Okay. Now minimum strength required in the other direction is given as uh, 0.25, that is 1/4 of the strength in the primary direction. All right, so that comes out to be 0.25 and 55 is the primary strength, that is the primary capacity in the other direction, that is 13.75. So obviously this is the minimum strength required in the other direction, and you already have a value of 19.8 which is greater than this one. So obviously the section that you have designed, it satisfies the requirement for the limit state of collapse. Okay, so now coming to the next step, that is check for limit state of cracking. Uh, Under the applied working moment, how much cracking or how much crack will appear, that you have to calculate. So again you have a general recommendation through which they have calculated the width of the width of the crack, which will be coming due to the working moment using this expression. Okay, so simply finding out this expression, you have a value of 0.035, and according to different codes the maximum crack width is less than uh, in this case permissible value of 0.1 millimeter is the maximum crack width the that can appear in case of aggressive environment. So this value is recommended by different codes. So in this value, in this case, our crack width is coming out to be 0.035 millimeter, which is less than the recommended value. All right. Now coming to the next step, we have check for torsion due to skew snapping of wires. So what does skew snapping means? Like I have discussed before as well, the poles are supposed to take supposed to carry the transmission wires, right? So in this case we have a twin conductor transmission wire. That means two conductors are passing through my pole. So now what happens if two diagonally opposite transmission wires, just try to imagine in your mind two diagonally opposite transmission wire snaps or breaks down or gets disconnected with the uh, Prestressed pole in some way. So then you have two disconnected diagonally opposite wires and two connected diagonally opposite wires to the Prestressed pole. So what this will do is basically this will create a torsion at the top of the Prestressed pole. All right. So how is it going to happen? The wires, diagonally opposite wires, are spaced at a distance of how much? 60 millimeter, I guess. In the problem it is given they are spaced at a, sorry, 60 centimeter apart. So that you have, then you have 600 millimeter distance between the twin conductor, that is this distance. So I'm asking ki say wires originating in this portion has one wires connected and wires originating in this portion has one way connected. So this will generate a torsion obviously, and the wires are carrying around 5 kilonewton uh, tensile strength, right? Tensile load, the tension in each conductor is given as 5 kilonewton. So you have a torsion of amount uh, 5000 is the newton that the tension load is carried by the wires, and the distance between them is 600 millimeter. All right, so if you multiply this, you have a torsional moment that is acting on the top of the pole where the dimension is 150 cross 200. Then you multiply that with 1.5 to get the design torsional moment. So you have 4.5 into 10 to the power 6 Newton millimeter. Now the section at the top is having a dimension of 150 millimeter by 200, and this needs to be checked for torsional stress. So how much torsional shear stress is coming? It is given by this expression here. H max is 200 and H mean is 150, which is basically the dimension of the section at top of the pole. So you have a torsional shear stress of 2.66 Newton per millimeter square. All right. Uh, so in this case, tau t, that is the torsional shear stress, is here, which is having a uh, value of 2.66. It can carry up to 5 Newton per millimeter square. All right. And the minimum value is given as 0.4 Newton per millimeter square. So in this case, you can see that uh, like if you compare this scenario with your RC design structure, where you have had a maximum shear stress, and then if it exceeds the maximum shear stress, then you had to redesign the structure. So in the same scenario, in this case it has not exceeded the maximum value. So you need not to redesign the whole structure again. But since it is greater than the tau t minimum, that is 0.4 Newton per millimeter square, you need to provide torsional reinforcement to support the structure against the torsional moments. All right. So in this case, what is going to happen? Basically, you have the tensile wires like this. So at the corners there will be a longitudinal bars that will be provided to support a transverse reinforcement in form of stirrups. All right. So to resist against the torsion, you have to give longitudinal reinforcement, uh, longitudinal reinforcement, and that will be supporting the stirrups throughout. All right. So So first you have to calculate the spacing of the stirrups, and it is done using this formula. What is x1 and y1 in this case? X1 and y1 are the distance that the stirrups will be, the length or width the stirrups will be having uh, from end to end. That is the spacing between the corner bars in either directions. All right. And rest of the parameters we already know. Simply substituting, we have a spacing of 127 millimeter. The cross section, then we calculate the cross sectional area that is required for the longitudinal bars. So since the torsional resistance will be carried by the transverse reinforcements, in this case the transverse reinforcements is also needs to be supported by the longitudinal bars, or which will be positioned at the corners. So simply by using this expression, you can calculate the area that is required for the longitudinal bars. In this case, it is coming out to be 488 millimeter square, and by simply providing four longitudinal bars of 12 millimeter diameter at the corners, along with the two links or stirrups, 12 millimeter two-legged stirrups at a spacing of 125 millimeter center to center will sufficiently take the uh, torsional resistance, will take the torsional moment that is coming uh, onto the top of the pole due to the skew snapping of the wires. All right. So these are the basic, some basic steps that you need to do while designing a pre-stressed concrete pole. So just summarizing, so we started with calculating the moments, working moments that is coming, and using that moment to design the sections. The moments are primarily due to wind loads, which is present on the exposed phase and on the exposed transmission wires. And then we checked for limit state of collapse and checked for limit state of crack. And finally, due to the skew snapping of wires, there is a possibility that torsions may develop at the top of the poles. So we had to check whether my section will be able to carry that torsional moment or not. In this case, however, the section was not able to carry on its own, so we had to provide certain measures against that in form of stirrups, and in combination with, to support that stirrup, in combination with longitudinal bars of 12 millimeter diameter as well. So there you have it. Uh, we have completed the uh, this problem on design of pole. So in the next video, I'll be discussing about the anchorage stresses in pre-stressed concrete.